Hello, my name is Edward Ramos, and I'll be talking to you about teixobactin and the importance of the large-scale synthesis of teixobactin as an antibiotic. So I just want to give you an overview of what I'll be talking about. First, I'll be talking about the recent increase in antimicrobial resistance and its effects on communities and populations around the world. And I'll also be talking about peptides and why they've proven to be untoxic and highly specific, and particularly why teixobactin and how teixobactin targets bacteria and acts as an antibiotic. Then I'll be talking about more of the chemical synthesis of teixobactin. Particularly, I'll be talking about teixobactin analog synthesis, and after I'll be talking about the important endurocytidine amino acid residue that's right here, and its scalable synthesis and why that's important to the actual synthesis of teixobactin. And teixobactin synthesis will be done using solid phase peptide synthesis. So here is the structure of teixobactin. It's an undeca peptide, which means that it includes 11 amino acid residues. Here you can see the ring associated with the peptide backbone or carbon backbone chain. And it's also considered a depsipeptide because it contains an ester bond between the, inside the carbon backbone chain of teixobactin. So the most commonly used antibiotics within the past few decades is penicillin, and even today it's most commonly prescribed as amoxicillin. And these inhibit the enzymes involved in cross-linking, the peptidoglycan layers. And what these enzymes do is they pretty much synthesize the cell wall of bacteria. And so penicillin inhibits these enzymes, and it doesn't allow the gram-positive and gram-negative bacteria to reproduce and continue to invade the human body. So here we can see the penicillin structure. This is the beta-lactam ring that's associated with amoxicillin and the penicillin-based antibiotics. And that is what is most important when it comes to inhibition of the enzymes that are involved in the cross-linking of the peptidoglycan layers. Now, an important thing to note is that penicillin-based antibiotics inhibit both gram-positive and gram-negative bacteria. Later on, we'll see that teixobactin only inhibits gram-positive bacteria. So recently, within the past couple of decades, penicillin resistance has become an issue not only because penicillin is being resisted, but other bacteria or other antibiotics are being resisted by bacteria. So I'm just going to talk to you about the penicillin resistance mechanism. So beta-lactamase is produced by the resistant strains of bacteria that are capable of resisting penicillin. Basically, what it does is it breaks the amide bond that's involved in the beta-lactam ring, and it reduces the carbonyl oxygen and the amine. So here you can see the reduced version of penicillin. And this completely inactivates penicillin and doesn't allow it to undergo its role in inhibiting the enzymes involved in peptidoglycan cross-linking. So specifically, the Staphylococcus species have become extremely difficult to inhibit. And in the 1950s and 1960s, there has been a pandemic community infection. And it was controlled temporarily by methicillin, but soon the Staphylococcus species, well, some strains of the Staphylococcus species became methicillin resistant. And these we term today, or we name them as community-associated methicillin-resistant Staphylococcus aureus, or, well, specifically the genus aureus of Staphylococcus species. Methicillin-resistant Staphylococcus aureus account for 90% of skin and soft tissue infections in the USA. And these can cause necrotizing fasciitis, pneumonia, and bone and joint infections. Tixobactin targets these gram-positive bacteria that, such as Staphylococcus aureus, by binding to lipid 2 and lipid 3, precursor molecules that are involved in the synthesis of peptidoglycan. So these crosslinks here are what amoxicillin prevent. So it begins by first cross-link, or peptidoglycan synthesis begins by first cross-linking transglycosylase, or cross-linking the N-acetyl glucosamine with N-acetylmuronic acid. And once they are linked, then cross-linking of the amino acids are done. What tixobactin does is it binds to the lipid 2 precursor molecules before the N-acetylglucosamine and N-acetylmuronic acid are linked together. And because of its mechanism, it has no detectable resistance by Staphylococcus aureus as of yet. And it may be because it's not affected by beta-lactamase. Because of these characteristics, pharmaceutical companies have a high demand for a synthesis, and particularly a large-scale synthesis of tixobactin.